have our lesson ready for today. However, it's going to cover about half of what we need to do the next mastery test. So we'll be finishing it tomorrow. So get your paper out. I really encourage you to go get some paper. I know some of you are taking notes like through typing. Um, it's going to be difficult, I think, to do some of these problems, these prints, these ideas on typing. So just get some paper and a pencil so you can take notes on this. In Edmentum, it's called using counting techniques to determine probabilities. What it's really going to be covering are these three topics below: fundamental counting principle, permutations, and combinations. Yeah, I would like it if you would, Antonio. Thank you. And you can jump in too and help me with some of the problems since you're already done with it, since you've already seen all this before, Antonio. Here we go. I'm going to start with an example. So in my box, I put three of your names, just picked randomly, and then popcorn and soda on the right. Suppose you three, Aaron, Manaya, Delaney, we're going to the movies, and you each were going to pick one item to buy, popcorn or soda. So suppose we have to pick one entry from each section. How many different total choices do we have? And here's an example. Here's what I mean by that. So for example, here's one choice we could make, one mix, Aaron with soda, or Aaron with popcorn. So Aaron could pick out just, I mean, obviously in real life you could get both, right? But let's say, for example, we have to only pick one item from each section. So there's two possible choices we have. Number one, number two. How many more do we have? See if you can tally those up and find the total number of possible options we have by mixing together these the people on the left and the foods on the right. And if you find the total, tell me in the chat. So 1 minute, go. Count them up, see if you can find them all, and then tell me the total number you get of total choices in the chat.
I'm sorry, can you repeat that?
Yes. We want to pick one entry. So one item, in this case, it's people. And then on the right, we've got food choices. So we have to come up with every different possible mix of one person with one food, one person with one food. How many total different mixes are there?
Oh, okay.
Does that help, Aaron?
Yeah.
I started our list already. So starting with mixing our people with the foods, Aaron could get a soda or Aaron could get popcorn. So there's two different choices that we could, maybe I should change my word. Instead of choices, let's say mixes. Mixes. So I want to mix one person with one food, one entry from each section. So picking one item from the left and one item from the right. How many total do we have? I see 4 people, or at least 4 comments in the chat. Nice. 5. Good. Count them out. And don't just try to keep track of it in your head. Write this down on paper. Otherwise, it'll get too much to keep track of. Let's see what you guys come up with. Oh, okay. So there's some stuff in the chat, but Looks like only Sela came up with 5 items. Good. Delaney came up with 4 different mixes. So I started with a smaller example with 3 items on one side and 2 on the other, so that we would be able to list these out. So let's try to list them all, and then we'll double check that we didn't miss any. Can we do any more mixes using Aaron? Meaning, is there any more that I missed that Aaron could have? Aaron has soda or Aaron has popcorn. Have we exhausted the Aaron list? And Aaron just said 6 total choices. Yes, good. We've exhausted the Aaron list. So we'll move on to the next person, Manaya. So Manaya could have popcorn and Manaya could have soda. You see? Are there any more that I could mix together using Manaya plus 1 food? No, right? So keep going. We got to do Delaney's list. Delaney plus popcorn, Delaney plus soda. So what I was hoping you would see here, because it's relatively small lists, right? We've got 3 items on the left, 2 on the right. We can list all of these out to see the total number of mixes that we're doing from the left list and the right list. And we see it's 6. There's no more mixes that we can make with 1 person and 1 food. Oh, it's okay. So good job. Thank you, you 3, Sela and Aaron and Delaney, for jumping in and trying that problem with me. So this is an example of what's called the fundamental counting principle. But we have a shortcut we can use for bigger problems, for bigger questions, with more items in each list. So real quick with me, notice how many items there are on the left list for people. There's 3 items in here, or 3 choices, 3 people. And then on the right list, we've got 2. Do you see a relationship between 3, 2, and then our total number of options that we came up with of 6 mixes? Do you see a relationship between those numbers? 3, and then a 2, and then a 6. Is there any math we could do to use 3 and 2 to get a 6? Let me ask again. What's the relationship, the math relationship between those 3 numbers, 3, 2, and 6? I know you see it, but how do we express that? Can I add the numbers, multiply them? Is there any relationship? 2 things in the chat. Multiply. Good, Aaron. Yes, you see it. So the choices from one list, there was 3 choices, times the choices from the second list, 2 choices, equals our total number of mixes, pulling one thing at a time from each list of 6. And this is the basics of the fundamental counting principle. Write this down. Fundamental counting principle. If there are P number of ways to perform one action, and if there's M number of ways to perform the second action, so this is like our 3 and our 2, 3 choices to pick a person, 2 choices to pick a food. Then there is P times M ways to perform both actions, to pick one of the actions, the second action, and mix them together. So there's a total number of P times M. 3 times 2 gave us that 6 ways to pick one person, one food. So copy this down, please. If there's P number of ways to perform the first action, M number of ways to perform the second action, there are P times M ways to perform both actions by mixing them together like we did with the people and the food at the movies. Next, we're going to do a larger example with more choices. And I want to show you it'll be too hard to list them all out for bigger problems. For the last one, it's relatively easy to list them out because there was only 3 in one list and 2 in the other. So we can sit here and make a list and know for sure and see them all laid out as options. But if we have more, yeah, go for it, Sella. If we have more items in our list, then this gets way too hard to list them all out. So here's a bigger example. Suppose we have these following choices to make a sandwich. So first box is breads. There's sliced bread and there's rolls. Second box is meats. And our choices are ham, turkey, or no meat. Skip the meat. So that's one of our choices, no meat. And then we have like veggies, lettuce, tomato, and avocado. And last up, we've got the condiments, mayonnaise and mustard. So if I wanted to do the same thing we did with the first example and pick one entry from each section, from each list, how many different sandwiches exist? How many different sandwich mixes can we make? If we use the fundamental counting principle, all we need to do is multiply the number of options in each section. So there's 2 options, then there's 3, then there's 3 again, and then there's 2. So using the fundamental counting principle, two times 3 times 3 times 2. So what is that? 6 times 6. 36 total different sandwiches exist here. And if we try making our list, you'll see it gets really hard to keep track of it. I want to just show you an example. So here's how we could start mapping them all out if we wanted to show all 36. We could have sliced bread with ham and lettuce and mayo. There's one sandwich. But we could also have sliced bread with ham again, with lettuce, and mustard. So there's just 2 of our possible sandwiches, right? That's 2 mixes, and it would get real confusing real fast to try to list them all out. That's why we're going to rely on the fundamental counting principle to see how many different total options there are, picking one thing from each list. So just like with the people at the movies example, if we just multiply the number of like possibilities for each action, the breads, the meats, the veggies, the condiments, and we multiply those numbers together, that tells us how many total mixes there are. And below, I started writing, here's our first sandwich or our first mix, our second one, and then we'd have to start over and do sliced bread, ham, and tomato and mayonnaise, sliced bread, ham, tomato, and mustard. So we don't want to rely on trying to map it out for problems like this. They're putting in a new air conditioner on top of the building, so it's like super noisy. Sorry if you can hear that. Any questions, guys, folks, before we move on? Okay, before we move on, show me your notes. I want to see that you guys have the last couple slides written down. So you have something to go back to. And if you need me to go back to it to see it again, just let me know. Aaron, thank you. Who else is here? Delaney, Antonio, Andrew, Sella, Keegan, and Bailey. All right. Do you need me to go back to see other pages, please? Okay. All right, so now we're going to look at a different style of question. So suppose we need to pick a smaller group from a larger group of items. Example. Okay, thanks, Andrew. I appreciate that. I see your message. So suppose we have a larger group of items, and we're just going to pick out mixes within that group, a smaller group from the larger. That's what I want to focus on here. Smaller group from the larger group. So suppose we're going to start with a small example with 3 students in a race, and I'm going to name these students A, B, and C, just to make it easy. So these are the 3 students right here. They're racing down the street together. How many ways can first and second place be awarded? So another way to ask this question is how many different variations of A, B, and C are there? Oh, Delaney, I didn't see, but I appreciate you telling me. And Keegan, thank you for sending the picture. So let me try to map this one out visually, and then we will learn another shortcut to answer this sort of question. So this time we're not drawing from different lists. We just have one list, one group of items, A, B, and C. And I want to pick from it a smaller group of 2. So for example, we could list them as they're listed already, A, B, and C. So this is like first place, second place, and then third place for poor old C. But that's just one way to list these 3 items. How many different variations of mixing the order of A, B, and C exist? So for example, A could come in first, B could be second, and C could be third. Well, what about A and then C comes in second and B is third? So here's the first way, the one way that we can award the prizes. The second way to award the prizes is A gets first place, C gets second, B gets third. And that would be the, I think that's the end of the options for having A come in first. So what about B coming in first? So B comes in first, then A, then C. Or B could come in first and then C and A. And we haven't done any where C comes in first. So then we could have C, A, B, or C, B, A. So see how I'm rewriting my original list and I'm really just focused on the first two. So I'm pulling, because we're only going to award 2 awards here, first and second place. So there's 1, 2, 3, 4, 5, 6 different arrangements we've come up with. 6 ways to award first and second. And just for another visual, imagine our larger group, the total number of like people racing, and it's a small number, but this is our larger group. The total is these 3 entries, these 3 people, A, B, and C, but we're pulling from that a smaller groups of 2, A, B, A, C, where this is like first and second. So we're pulling from it smaller groups of 2. BA, BC, or CA, CB. So I just kind of rewrote the first list we made to emphasize that we're really just focused on pulling 2 from a total of 3. And the order matters. Because it's different if, for instance, here, this entry, A comes first, then B, and then below it, we've got B coming first, then A. Notice that both of those entries I pointed at, they each have the same elements. They each have A and they each have B, but the order matters because one's first place, one is second. So in this example, we pulled groups of 2 from a larger group of 3, and the order matters. The order matters from our context of we're giving out an award. So it's like it's different, right? It matters to you if you get first or if you get second place. This is an example of a permutation. I'll hold the screen for a little bit, and then we're going to define permutation and show the formula for it. So like I've been repeating, permutation is pulling a smaller group, R, from a larger group, N. And this is important when order matters. So in that last example, we wanted to pull 2 groups of 2. That's our R. From the larger group in that example was 3, the total people. That's our N, and order matters. I want to do the formula with you, and we have to have a definition, and then we'll do another example of figuring out a permutation with a larger set of numbers. Oops, sorry. So here's our formula. Permutation, whenever we have to pull smaller group from a larger group and order matters, here's how it's written. N, capital P, R. And how we say this is n choose r. Our group is, the large group is n, and we're choosing or picking smaller groups of r in the formula. N factorial, we're going to define this in just a second. That's the exclamation point. N factorial over n minus r factorial. Make sure to write down this formula and the definition above it, pulling a smaller group r from a larger group n when order matters. How we say this on the left is n choose r, or n pick r. And it's equal to n factorial over n minus r factorial. Now let's talk about factorial. Factorial is another operation. It's one we don't teach in like elementary school because it's confusing. So now you guys are at the stage you're ready for factorial. So instead of adding, subtracting, multiplying, and dividing, it's like these, but it means something else. So how do we compute or figure out or simplify a factorial? What does it mean? So whenever we have the exclamation point, the factorial, what it means is it's the number factorial times the, sorry, let me fix that. It's n factorial would be defined as the number n times the next number down times the next number down below that, and so on. All the way down to 1. So here's an example of a factorial. If we needed to do 10 factorial, well, we'll do 10. 10 factorial, well, this would be defined as 10 times 9 times 8 times 7, all the way down to 1. Now I'm going to change my color, and I want to connect this to that last example where we had 3 people running in a race and we picked 2. So we just, for that last example, we listed them out. But for larger numbers and larger problems with not just like a group of 3 things and we're picking 2, we're going to want to rely on using this the permutation and the factorial to figure out problems that are larger. So to connect it back to the runner example, we did 3 pick 2. 3 is our bigger group, 2 is our smaller group. So if I plug those into the formula, it's 3 factorial over 3 minus 2 factorial. And here's how we can simplify this. So on the top of the fraction, we have 3 times 2 times 1. On the bottom of the fraction, we simplify inside the parentheses, so do the subtraction. 3 minus 2 is 1. And then it's factorial of whatever's left over, which is 1 factorial. So simplify the top now. It's 3 times 2 times 1, so that's just a 6. And in the bottom, 1 factorial would just be 1. So this question kind of cleaned up rather quickly. It's equal to 6 when we're done simplifying the fraction. When we listed all of those options for ABC, ACB, BAC. Remember that list? We counted 6 total. BCA, I'll finish the list just to connect it. BCA, and then CAB, CBA. So there's 6 items in the list when we were able to count them out. And that's where this 6 is coming from using this permutation formula. Let's do another example of a permutation. We're going to have a larger group R, and a larger group N, and we want to pull a smaller group R from it. So a big group of numbers or items, picking a smaller sets of those at a time. Okay, we're going to do it here. So here's our next permutation example. Suppose we have 5 items in our larger group. And let's list them out. Let's just use letters. So our 5 items will be A, B, C, D, and E. Pick groups of 3. And the order matters. So let's start listing them to get an idea of what we're doing, and then we're going to use the permutation formula to find the final answer. So if we're picking groups of 3 out of these 5, one smaller group of 3 that we could pick would just be A, B, C. We could also say A, C, B. I haven't even used D and E, right? We haven't even looked at those yet. But here's 2 different groups of 3 that we could draw from that larger group of 5. There's also A, B, D, A, B, E, and those are, I think, all the ones. No, that's not all the ones. That's not even close. That's all the ones that start with A and B. A, B, C, A, B, D, A, B, E. So I should back up and do the ones that have start with A, C. So in fact, sorry about this. For those of you taking notes, I am going to erase the second line. We're going to write it next to it. Okay, so here's the first list of just starting with A and B. A, B, C, A, B, D, A, B, E. And then we'll switch over since we've exhausted. Yes, we've exhausted the list that starts with A and B. So what about A and C? A, C, B, A, C, D, A, C, E. See how, I'm not trying to make it confusing, but I wanted to point out to you that it is confusing. And listing, even just trying to pick groups of 3 from a total of 5 is starting to get really confusing and really hard to keep track of. It's possible to do, right? Definitely possible to do. But because it's confusing, this is why we're going to rely on our formula. So let's try doing this question using the permutation formula now. The list is longer than what we have here, but it's getting hard to keep track of. So because it's hard to keep track of, let's try using the formula. So we want to do the permutation formula, but our larger group is 5. So 5, pick 3. picking groups of 3 from a larger group of 5. We're going to fill in our formula. So it's n factorial, 5 factorial over 5 minus 3 factorial. So start by expanding the top. When I say expand it, because we're dealing with the factorial operation, I mean rewrite it instead of 5 factorial as 5 times 4 times 3 times 2 times 1. Excuse me. And then simplify the parentheses. So 5 minus 3 is 2, right? So we have 2 factorial in the bottom. We can expand the 2, and really it's just 2 because we don't need to show the times 1, but let's do it anyways. So 5 times 4 times 3 times 2 times 1 over 2 times 1. So now I want to cancel whatever's matching on top and on the bottom. Remember, anything divided by itself is 1. So 1 over 1 can cancel. 2 over 2 can cancel. And what's left? 5 times 4 times 3. And what is 5 times 4 times 3? 20 times 3. So it's 60. There are 60 different, this means there are 60 different smaller groups of 3 that we could pick from the larger group of 5. And that's why I don't want you to try to list them all out. I mean, I just don't want you to spend your time doing that. So it's possible, right? We could find all 60 different mixes like I started doing over here on the left. I only found 6 and I gave up because it's already getting crazy. If we can use our formula, it'll tell us pretty fast with a little bit of math how many total groups there are. Before I move on, because there's one more thing to do for today, are there any questions or concerns on the fundamental counting principle from the beginning, or the permutation formula, or the examples? Or on using the factorial? Your mics are off. At home, I want you to practice saying this language, factorial. Factorial. In permutation. Oh, and I'm spelling it wrong. Nice. I'm sorry. At the top, permutation. This is a permutation. Permutation. Okay. No questions. Then let's look at our next topic. So I'm going to start with an example. Suppose we need to pick a smaller group from a larger group of items, and the order does not matter. And this is key. The order does not matter now. How many combinations exist pulling 3 items from 5 total, and the order doesn't matter? Again, I want to just use our letters as our items to pick from. So in the total items of 5, we've got A, B, C, D, and E. But now the order doesn't matter. So for example, we're doing groups of 3, picking groups of 3 from this 5. So since order doesn't matter now, A, B, C is basically the same. It's the same group as A, C, B and C, B, A and BCA. These are all the same now because the order doesn't matter. We're just like saying if we have the A in it, the A, B, C in it, it's all the same. So this is very similar to the permutation, except the order doesn't matter. The formula for this is called the combination formula. So we've looked at permutations, and that's when order does matter to your list, to pulling the items. And then now we're going to look at combinations when order doesn't matter. So the definition for a combination is almost the same. Pulling a smaller group R from a larger group N, but order does not matter. So like the permutation formula, this looks similar to the first one. So it's N capital CR, and how we say this is N choose R. From the larger group of N, we're pulling smaller groups of R. The formula also looks very similar. It's N factorial over R factorial times N minus R factorial. The difference between the combination formula and the permutation formula is that we're also dividing by that extra R factorial right here. That's the only difference. Because we're dividing by that extra number, though, combinations will be smaller than the permutations because order doesn't matter for a combination. Sorry. So let's try to answer the combination question using the formula. So we had a group of 5, total of 5 items, picking 3 at a time. And the order doesn't matter. So we're doing 5, choose 3. So notice instead of the capital P, it's the capital C. And we're going to use this correct formula. So 5 factorial over 3 factorial times 5 minus 3 factorial. So this time there's a third factorial we have to deal with as well. Notice that there's 3 exclamation points here. So expand the top. Always start by doing that. 5 times 4 times 3 times 2 times 1. But I'm going to start skipping putting the times 1 in there because it's just a 1. We don't need it. And then expand the 3 factorial below. That's 3 times 2. And in the parentheses, 5 minus 3 is 2. So we've got a 2 factorial. We'll expand that. 5 times 4 times 3 times 2 on top. We've got a 3 times 2 in the bottom. And then for the 2 factorial, that's going to be 2 times 1, or just plain old 2, just 2, because we don't need to show the times 1 anymore. So now we're going to cancel and simplify everything we can. I'm going to change to red. So notice we've got a 2 in the top and bottom, so they can cancel. We've got a 3 in the top and bottom, they can cancel. And then we've got a leftover 2 in the denominator in the bottom, right? There's nothing to cancel it with, but I can reduce 4 divided by 2. 4 divided by 2 is 2. So there's a 2 left over on top. For that, I divided just 4 over 2. What's left over here that's not crossed out? 5 times 2, which is just 10. So this means that there's 10 different ways to pick 3 items at a time from 5. And the order of picking the items doesn't matter. Okay, one last thing I want to do today in our next 5 minutes is kind of do a comparing of a smaller problem again, of a permutation and a combination for the same problem. And I want to do a smaller problem so we can actually list them out and see how the order matters on one set and the order doesn't matter on the other. So let's start with 4 items this time. We have 4 items, A, B, C, and D. Let's pick groups of 2. From the 4. So let's start by doing the formula, permutation formula, and then on the right we'll do the combination. Permutation, and then over here we'll do combination. So permutation means the order matters. So let's try the problem picking groups of 2 from a total of 4. How many different ways are there to list groups of 2 from 4? So that's 4, pick 2. So 4 factorial over 4 minus 2 factorial. Expand the top, 4 times 3 times 2. Do the subtraction and then expand the bottom. 4 minus 2 is 2. So this turns into 4 times 3 times 2 over 2. Cancel whatever you can. So we can cancel the 2 over 2 here, and we're left with 4 times 3, we're left with 12. That's not too big, right? 12 things, we should be able to list those. Let's actually try to list them just to kind of keep track of these 12 different ways to pick 2 from the 4. So below now, I'm going to list those out. So start with the first one. We'll start with A. There's AB, AC, and AD. There's no more pulling 2 items from the 4 that begin with A, right? There's no AA. There's not a second A in there, so we stop there. AB, AC, AD. Now let's start with the B's. So BA, BC, BD. And there's no more ways to pick 2 items from the 4 that begin with B, right? So we're done. We can move on to C, CA, CB, CD. And now for the D's. So DA, DB, DC. And there's our 12 items. Or 12 groups of 2 from the 4 when order matters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now on the right, let's do the same problem, but in a combination where the order doesn't matter. So we're going to do for choose 2. It's almost the same formula, except we're also dividing by an extra r factorial. All right, always begin by expanding the factorial. 4 times 3 times 2. On the bottom, we've got 2 times 1 for that 2 factorial. So I'm just going to say 2 times the parentheses. 4 minus 2 is 2. And now we'll expand that part. So 4, 3, 2 over 2 times 2. 2 over 2 can just straight up cancel. 4 over 2 can be divided. 4 divided by 2 is 2 on top. So I'm kind of dividing and canceling that 4 over 2. That becomes a 2. And there's our 2 times 3. So this says there's 6 different ways to pick 2 items from the 4, and the order doesn't matter. So we can find these 6 groupings by looking at our purple list. But notice, like on the left side of the screen over here, AB, that's one choice. And then next to it, we have BA. When the order doesn't matter, these are the same choice. It's the same combination, right? AB, BA doesn't matter. So AB, AC, and AD. And we're not going to list BA, CA, and DA because they're the same to us now. So we can mix B and C together, and we can mix B and D together. And we can mix C and D together. And that's it. There's our 6 groups of picking 2, or choosing, I should say choosing 2 from 4. So combinations will always be smaller than a permutation. We did it one way, permutation, we got 12. We did the same problem with a combination, we got 6, because we're essentially canceling out all the repeats that we have on our purple list. Tomorrow, we need to add a little more to all of these ideas. And then we'll be able to do probability problems using our permutations and our combinations and the fundamental counting principle. So for today, honestly, there's no new homework. We're not ready to start the mastery test based on just this. So tomorrow, join me again at 10. We'll finish this lesson and then do our mastery test using these ideas, okay? That's it for today. Have a great day. If you want to see any of the notes before you go, just let me know and I can go back. Otherwise, I'll see you tomorrow, okay?
Take care.
You too.
All right, bye.
Bye, Aaron. Bye, Keegan.